So what we are going to talk about today is the response of series RLC circuits. And this is going to be very similar to what we saw with parallel RLC circuits prior to the break, with one important exception. So let's start with a simple circuit where we have some voltage source, let's call it Vs, like so. And then we have a switch, and let's say for the sake of argument here that we'll be dealing with a natural response while we derive this thing. So our switch is going to open, removing our source from our circuit, which consists of a resistor R, an inductor L, and a capacitor C, like so. And I'm going to define my inductor current flowing in this direction, IL of T, such that the voltage drop over my inductor VL of T will have this polarity. The voltage drop over my capacitor VC of T will have this polarity, and the voltage drop over my resistor R of T will have positive polarity on bottom, negative polarity on top, so that our inductor current IL of T will flow into the positive polarity terminal of all of the elements during the transient condition, right? So while our switch is closed, it should be fairly obvious in this particular circuit, right? So with our switch being closed, we would observe, or if it's been closed for a very long time, that our inductor and our capacitor are going to look like their DC steady state equivalents, which would be a short circuit for the inductor and an open circuit for the capacitor, right? So from that, after the switch has been closed for a very long time, we should see that our capacitor has a voltage of Vs over it. So it has some amount of stored energy. And then as we open that switch up, the energy from the capacitor will be transferred to the inductor and the resistor. And we'll see a very similar situation as to what we saw when we had the elements connected in parallel. So during the transient condition, after our source voltage has been removed, we can write a Kirchhoff's voltage law equation around that loop, simply saying VR of T plus VL of T plus VC of T is equal to 0. And now we can use our current voltage relationships for capacitors, inductors, and resistors to express all three of those voltage drops in terms of that common inductor current IL of T. So using Ohm's law, we should have R times IL of T is our voltage drop over our resistor. The voltage drop over our inductor will be L di by dt, and the voltage drop over our capacitor will be 1 over C, the integral from 0 to T of IL of x dx, where x is simply a dummy variable for time, plus VC at 0, which is our initial condition on the system, equal to 0. And we now have, again, an integral differential equation that we are going to make a second order differential equation by taking the integral, or excuse me, the derivative of both sides. And if I do that, what I will find is that I'll get L times the second derivative of the inductor current plus R times the first derivative of the inductor current plus 1 over C times the inductor current itself is equal to 0. So we have a homogeneous second order differential equation. And we're going to use effectively the exact same guess value that the correct response of this is going to be of the form of an exponential function, right? So if IL of t is of the form AE to the ST. Oh, actually, let me do one more thing here before we take this or make this substitution. I'm going to divide everything through by L so that the coefficient of my second derivative term is 1. So that's just going to take this L here and give me R over L here and 1 over LC there. Everybody okay with that? So when I do my substitution, I'm going to have S squared A E to the ST plus R over L times S AE to the ST plus 1 over LC AE to the ST is equal to 0. Grouping like terms, this is going to look like A times S squared plus R over L times S plus 1 over LC, all multiplied by E to the ST is equal to 0. And I now have my characteristic equation, which is again a simple polynomial. All right. So it's a second order polynomial. So it should have two solutions. S1 comma 2 will be equal to negative B. So that's negative R over L plus or minus the square root of B squared. So that's R over L quantity squared minus 4 times A times C. So that's 1 over LC goes here, all divided by 2, which I can make look like negative R over 2L plus or minus the square root of R over 2L squared minus the square root of 1 over LC quantity squared. So I've effectively made it look like the same form. We can easily identify then that for our series RLC circuits, alpha is simply R over 2L, and omega naught is again the square root of 1 over LC. Everything else about analyzing a series RLC circuit is literally the exact same thing, okay? So when alpha is greater than omega naught, we have an overdamped circuit. When alpha is equal to omega naught, we have a critically damped circuit. When alpha is less than omega naught, we have an underdamped circuit where omega d is still simply omega naught squared minus alpha squared, square root of that whole thing. Everything else is exactly the same. The only change in the analysis between a series RLC circuit and a parallel RLC circuit is that we use a slightly different equation to determine our alpha value for our Neper frequency. Everything else, I cannot repeat this enough, is identical. So do we need to go through all of the rest of the derivation crap again? Or can we just work an example problem or two? All right, so let's go to the example problems here. All right, so let's say that I have the following circuit. This time, let's have it in such a way that our switch is closing at t is equal to 0. Let's call this 5 amps for the sake of argument. All right, somebody give me two values for resistors. 10K and 20K. Give me a value for an inductor. Okay, that's not a number. 23 what? What are my units? For an inductor. 23 henries. All right, that's a really big inductor, but sure. All right. Light inductor. Somebody give me a value of her capacitor. Sarah. 3 farads. All right. That's a really honking huge capacitor. That's okay. I don't know, something around the size of this room, but that'll be all right. This is just math. Okay, so let's define our inductor current. IL of t like so. So this is going to be VL of t. This is going to be VC of t. And I'm going to choose my resistor voltage VRT to be positive polarity on top. We'll work our way through that in a moment. Okay. So let's figure out what our quantities of interest in this problem are going to be. I'm going to say for sure that I want to know what my resistor voltage V of t is, and we'll talk about how to solve for that quantity based on what you tell me the other quantity needs to be. So your options are inductor current, inductor voltage, capacitor current, capacitor voltage. Pick one. Capacitor voltage. All right. Okay. That's the arguably hardest possible quantity to solve for to figure out what the resistor voltage is, but it's not that much harder, so it'll be okay. All right, so what did we do first last time, right? Did we analyze the circuit at t is equal to 0, all that kind of stuff, and then figure out whether it was overdamped, underdamped, critically damped? All right, let's do that same process here. All right, so at t is equal to 0 minus our circuit, well, actually, we could pretty much do this guy by inspection, right? So I want to know what my capacitor voltage is at 0 minus what my inductor current is at 0 minus, and really I don't need anything else past that, but we could take account of it. All right, the reason why I'm saying that we can analyze this by inspection is because our switch was open at t is equal to 0 minus, which means our series RLC circuit on the right-hand side was disconnected. So it stands to reason that all of our initial conditions are 0, right? So we can say that VC of 0 minus is equal to VL of 0 minus is equal to 0 volts. And IC of 0 minus is equal to IL of 0 minus is equal to 0 amps. We don't need to do any actual analysis here. So let's move along to at t is equal to 0 plus. So at t is equal to 0 plus, now our current source and 10 kilo ohm resistor are being added into the circuit. Let's see. So we know that our inductor current was 0 amps. So what am I going to replace my inductor by here? An open circuit, because we need to ensure that 0 amps of inductor current continues to flow. And say IL at 0 plus must be 0 amps. My capacitor voltage was 0 volts. So what should I replace that with, Alexis? So the capacitor voltage is the quantity that can't change abruptly, right? So if the capacitor voltage was 0 volts at t is equal to 0 minus, it has to continue being 0 volts at t is equal to 0 plus. So my question to you is, what do I replace that capacitor with in my t is equal to 0 plus analysis? It'd be a short circuit, because a short circuit has exactly 0 volts and any amount of current can flow through it that needs to, which is exactly what describes our capacitor, right? We know that the voltage drop is 0, so we'll replace it with a short circuit. All right. All right, so since we're solving for the capacitor voltage, we know that VC at 0 plus is still 0 volts. We can say that IC at 0 plus, which is the same thing as IL, has to be 0 amps. Just for the hell of it, although turns out we're actually not even going to use this, what would VR of 0 plus be? Disagree wholeheartedly that it will be 0. So the voltage over the capacitor can't be in parallel because there's this open circuit here that's breaking that connection.
I mean, like, in terms of the open circuit here, I mean, like, the capacitor voltage would just be what's over the 20 kilo.
I disagree. Kirchhoff's voltage law will tell us that that can't be true, right? Our capacitor voltage was 0 volts at t is equal to 0 minus. Okay, let's scroll up and make sure that we all agree on it. Okay, so at t is equal to 0 minus, this switch was opened up, which means that this resistor, this inductor, and this capacitor were not connected to a source at all. So by simple inspection, VC has to be 0, and IL has to be 0. VL would also be 0. IC would also happen to be 0. And then VR and IR, regardless of which way we define their polarities and directions respectively, would also need to be 0, okay? So we know definitively that the capacitor voltage at T is equal to 0 minus is 0 volts, and the inductor current at T is equal to 0 minus is 0 amps. Those two quantities cannot change abruptly, which means whatever value they have at T is equal to 0 minus, they have to continue to have at T is equal to 0 plus, which is how we're analyzing this, okay? So I know that my inductor current is 0 amps because at T is equal to 0 minus, it was 0 amps. My inductor voltage can change, right? So let me say what I mean by that specifically. Let's put it in here in red. This is my inductor voltage at T is equal to 0 minus, or 0 plus, excuse me, right? This quantity does not have to have the same value that it had at T is equal to 0 minus. Similarly, my capacitor current, which I'll draw here, I see at 0 plus, doesn't have to have the same value. Now, in this instance, it does, because we know that no current is going to be able to flow through that open circuit, okay? But I would argue that our inductor voltage is going to change rather significantly, right? So our capacitor voltage is 0 volts, but I would argue that our resistor voltage, VR, is very much not. Let me define it, right? And the reason why I say that is if we look at this 5 amp source, some of the current flowing through the 5 amp source is going to split off and flow through the 10 kilo ohm resistor. Some of it's going to split and flow through this 20 kilo ohm resistor, and then it's going to recombine. So since there's current flowing through the 20 kilo ohm resistor, there must be a voltage drop over the 20 kilo ohm resistor. The way that this circuit is connected, based on the initial conditions that we saw, it's the inductor that's actually in parallel with the 20 kilo ohm resistor, not the capacitor. Okay. So VR, which will be exactly equal to VL, at 0 plus, is going to be 5 amps times, let's see, so 10 times 20 is 200 over 10 plus 20 is 30 kilo ohms, which is going to be 1,000 over 30 volts. Or will that be kilovolts? Well, what ridiculous amount of voltage, because we're pushing a very large amount of current through a kilo ohm size resistor. Okay, so we have a crap ton of voltage here. Doesn't particularly matter for the math or anything like that. We're dealing with all ideal quantities, so it is what it is. All right. As I said a little while ago, we're actually not even going to wind up using this value, but we could if we work the problem in a slightly different way. All right. So how do you guys feel about our analysis at T is equal to 0 plus? Everything seems reasonable. All right. Now we analyze the circuit at T is equal to infinity. We have to do a T is equal to infinity analysis because we have a source still in the system at T is equal to infinity. So at T is equal to infinity, we're going to have our 5 amp source here's our 10 kilo ohm resistor. Here's our 20 kilo ohm resistor. What should our inductor look like at T is equal to infinity? Sonny, you got any thoughts? I disagree. So at t is equal to infinity, that's a long time after the transient condition has died out, which means we're back at DC steady state. So we should use our DC steady state equivalent for an inductor, which is a short circuit. So our inductor is a short circuit. This is our current IL at infinity. Our capacitor will also be its DC steady state equivalent, which will be an open circuit. So here's our capacitor voltage VC at infinity. And here's VR at infinity. So somebody tell me what some of these values are going to be. Start with something easy. Our inductor current, which is identical to our capacitor current at infinity, has to be what? 0, because our capacitor looks like an open circuit, and so no current can pass through it. So based on that, what should our capacitor voltage be at infinity?
1,000 over 30 again.
Exactly right, 1,000 over 30. And that's amps times kilo ohms, yeah, which should be kilovolts. And what would VR be in this case? Exact same thing. All right, everybody okay with our analysis at t is equal to infinity? All right, so now, based on the numbers that you guys have chosen, let's see if this circuit is critically damped, underdamped, or overdamped, right? So alpha is equal to R over 2L. My question to you guys right now is, what's R going to be? Pardon?
Would you combine the resistors with use the 200 over 30 value?
Yes, perfect, absolutely perfect, okay. So yes, you would combine the 10 kilo ohm resistor and the 200 kilo, or excuse me, the 20 kilo ohm resistor together, because both of those resistors are in the circuit during the transient condition. They're connected in parallel. So the equivalent resistance seen by our energy storage elements, our capacitor and inductor, is 20 kilo ohms in parallel with 10 kilo ohms, or 200 over 30 kilo ohms. Everybody okay with that? $200 over 30. Sorry, that's just R. Divided by 2 times L. I believe Cheston chose L to be 23 henries. So that's 2 times 23 henries. So it seems like alpha is going to be really big. So 200 over 30 times 10 to the 3 divided by 40. Well, my calculator turned off. Guess it somehow ran out of batteries. Let me put it in the light. Somebody else tell me what the answer is supposed to be.
144.93.
144.93 Neppers So 200, should that be 144.93 times 10 to the 3?
That's not, I got the clean 144.
Okay,
That's 8 kilo ohms roughly. So it's been 8,000 over 40.
okay. All right, units are wonky here, so I just wanted to make sure things are legit. All right. Omega naught is going to be the square root of 1 over L, which is 23 henries times 3 farads. So this is going to be significantly, well, I don't know, significantly, it's going to be less than 1, obviously. 0.1204 radians per second. Okay. All right. So alpha is obviously larger than omega naught, which makes this circuit overdamped, underdamped, or critically damped. Overdamped. Yes, rather damped. All right, so since we have an overdamped circuit, that means that we're going to use the overdamped response equations, right? So is it okay if I move to the next page on my tablet here? All right. So we know that our capacitor voltage VC of t will be of the form A1e to the S1t plus A2e to the S2t plus VC at infinity. So before we calculate or do the simplification here, obviously we're going to wind up needing to know what S1 and S2 are. So let's go ahead and take a moment to calculate those two guys, right? So as a brief aside, S1 is negative alpha plus the square root of alpha squared minus omega naught squared. And S2 is going to be negative alpha minus the square root of alpha squared minus omega naught squared. So it looks like S1 is going to be pretty close to 0, and S2 is going to be pretty close to negative 2 alpha, just since alpha is so much larger than omega. Somebody give me
Negative 389.
for which quantity?
Oh, no, that is actually
Negative what?
289. 0.855.
All right.
And then for S1, I got negative 5 times 10 to the negative this.
Negative 5 times 10 to the minus 5 per second. All right, that seems reasonable to me. S2 should obviously always be much more negative than S1 because we're subtracting a quantity from alpha or negative alpha. So S1 and S2 are the eigenvalues of our system, so they tell us how the different parts of our response exponentially decay. Right, so that's what we're going to put in here to figure out what our capacitor voltage is. And they'll pop up as portions of coefficients in a system of equations that we're going to be forced to solve because we have an overdamped response. Okay. So with those two quantities out of the way, what does our response equation simplify to at t is equal to 0? So if we put 0 in here and here, what do we wind up getting? Exactly right. A1 plus A2 plus VC at infinity. And we have numerical values for VC at 0 and VC at infinity, right? So VC at 0 was 0 volts is equal to A1 plus A2 plus 1,000 over 30 kilovolts, which means A1 plus A2 must equal negative 1,000 over 30 kV. Everybody okay with that? Our capacitor current, IC of T, using my table here, will be of the form S1 A1 E to the S1T plus S2 A2. Actually, I need to put brackets around this. E to the S2T, and this whole thing should be multiplied by C. So I apologize. I used the derivative part directly from the table, but I made a slight mistake here because I forgot, let me do this in blue, that IC of T is C dV by dt. So I need to make sure that I multiply my derivative relationship for my table by that coefficient C. All right, so IC at 0 plus is just going to be C times S1 A1 plus S2 A2. Since IC at 0 plus was, let's see, what did we find it to be? 0 amps. Turns out that having the C included doesn't actually do anything to us here. So it would have been okay to forget it in this very specific case. Generally speaking, it's a terrible idea to forget it. So I'm glad that I caught it, but it would have worked out. Okay. So we can see that S1 A1 plus S2 A2 is equal to 0. And we now have two equations, two unknowns, right? So this is our first equation. This is our second equation. Somebody tell me what A1 and A2 are based on solving that guy.
One is
27.712. All right.
I got negative 33,361.
Negative 33,361. Okay. What should my units for these coefficients be? I disagree. Let's scroll up here. We could do dimensional analysis and figure it out, but they're volts because it's something times an exponential function plus something times an exponential function plus voltage equals voltage. So A1 and A2 need to have units of volts. And we would get exactly that if we did the dimensional analysis of all of those. C times S1 bit would get us there. So this is units of volts, and this is units of volts. So from this, VC of t will be 27.712 e to the negative 5 times 10 to the negative 5 t minus 33,361 e to the minus 289.855 t plus 1,000 over 30 kilovolts. I added my VC at infinity, correct? So what I want you guys to do, just to make sure everything's hunky-dory, is just add these coefficients, right? 27.712 minus 33,361 plus 100, or excuse me, 1,000 over 30 times 10 to the 3, and make sure that that's pretty close to 0. There's going to be a little bit of rounding here.
-0.2.
-0.2, so millivolts off seems, or you know. All right. So that's what our capacitor voltage is going to look like. All right. So
Does the exponential have units itself?
the exponential bit, no, absolutely not. The exponential acts on a unitless quantity, right? So this negative 289.855 is one of the two natural frequencies of the system having units of per second. Time is measured in seconds. So our exponential function is acting on an argument that is unitless. So this just represents a number that is scaling the value at 0 by some amount as time progresses. All right, so the other quantity that we were interested in is the voltage drop over our resistor. So let's scroll all the way back up and think about the different ways that we could solve for that quantity. Okay. So off the top of my head, there are two ways that I can solve for it, but I want to talk about why we can't use the methodology that we use to solve for the capacitor voltage to get it, because that's actually pretty important. And I see some students try to do that, even though I tell them very explicitly it cannot be done, right? So the analysis that we're doing here to determine our capacitor voltage, and it would have been effectively the exact same analysis if we were trying to determine our inductor current, involves exploiting the derivative-based relationships and the initial conditions on the system. There is no derivative-based relationship between current and voltage in a resistor, which means we can't use this methodology. We have to know what the capacitor voltage is or the inductor current is to figure out what's going on with the resistor, okay? Because Kirchhoff's current law is going to force whatever is happening to the resistors. Something similar to that is going to happen, excuse me, whatever's happening to the inductor, something similar is going to happen to the resistor. Similarly, Kirchhoff's voltage law is going to force whatever the voltage drop over the capacitor is to be of that general form for the voltage drop over the resistor, right? So with that being said, and we have no way of using the same method of analysis, we're going to have to go back and rely on those types of relationships, KCL and KVL, right? So we could see here pretty easily that VR, the voltage drop over our resistor, is going to be VL, the voltage drop over our inductor, plus VC, the voltage drop over our capacitor. Well, we know what VC is, but we have no idea what VL is. So that, I would argue, is probably not the easiest way to determine the quantity, because then we're going to have to go do a whole bunch of work to figure out what VL is. Another way would be to observe that this current IL, which is the same thing as the current IC, is flowing into the negative polarity terminal. So VR should just be 20 kiloohms times negative IC. And while we don't know IC explicitly, we do have all of the pieces of information that we need to solve for it rather trivially, okay? So Okay, write that in blue here. I'm saying VR of T is just negative 20 kiloohms times IC of T using Ohm's law. Ian, are you raising your hand?
Yes. Would we be using the 10 kilohms or should we use the combined resistance?
Oh, fantastic, fantastic point. You're absolutely right.
Consider the 5 amps.
Yes, yes, we do have, oops, what the heck just happened there? Sorry, hold on. No, you're absolutely correct on all of those points. So let me go to my next page. Yes, all right. Yeah, if this were a natural response problem, which is where my head was at, that's correct. But you are absolutely correct in as much as we need to know what's going on totally here, okay? So the voltage drop over the resistor is going to be some combination of what's being caused by the 5 amp source and what's being caused by the energy storage elements. Okay, so let's think about this then.
You'll use scale because combining them will have the same voltage over the equivalent.
Okay, so let me redraw something here just real quick, like, just so I can wrap my head around it. I'm just going to call this guy REQ. $23 Henrys, 3 farads. And so this is my current IL of T, which is the same as IC of T. Let's call this current right here IR of T. And let's call this guy right here VR of T, which is what we're trying to solve for, okay? So VR of T is obviously REQ times IR of T, or REQ. And so now we got to figure out how to find what IR of T is. Well, IR of T is just 5 minus IC of T. All right, that should get us our voltage. And there we go. Okay. Thank you for pointing out my mistakes, legitimately. All right, so we can now see fairly easily, again, that the voltage drop over the resistor R has some dependence on IC of T. So let's talk about how we can use the information that we currently have to figure out what IC of T is. Let me scroll down to our analysis, right? So IC of T is just C, which we know, multiplied by S1, which we know, multiplied by A1, which we know, e to the S1T, plus C S2A2 e to the S2T. So we have all of the parts to plug in to figure out what IC of T is fairly trivially, right? So IC of T is C S1 A1 e to the S1T plus C S2 A2 e to the S2T. So somebody whose calculator is presently working multiply C times S1 times A1 and tell me what that number is supposed to be. So C was 3 farads. S1 was 5 times 10 to the minus 5. A1 is 27.712. 12,048.7. E to the negative 5 times 10 to the minus 5 T. And then what is C times S2 times A2?
Oh, that is wrong. I'm sorry. I used alpha instead of S1.
All right, let me erase that.
It was 4.157 times
4.157 times 10 to the minus 3. So that bit looks like it's in milliamps. All right, what about the next bit?
So it'll be positive 29 million. 9,000.
E to the negative. Let's see, this was 259.855 T. Amps. All right, so let's think about this just real quickly. All right.
That first term is negative, by the way. The million.
So at T is equal to 0, this capacitor current, if I'm not mistaken, let's scroll up here. So at T is equal to 0 plus, our capacitor current was 0. So we have a bit of a problem. Yeah, I mean, it is in as much it's possible to analyze. Having a 23 Henry inductor and a 3 farad capacitor are very extraordinarily unlikely, but there's nothing that says that our analysis shouldn't be working here, which leads me to believe that we have either miscalculated the quantities A1 and A2, or we have miscalculated our quantities S1 and S2. So can somebody with a TI 36 let me borrow it for about 3 minutes?
It's just a modern, yeah. This is the exact thing.
Yeah, I'm gonna use somebody else. I can't use that. Over the break, I managed to get my 991 out of the package and never even turned it on. All right, so S1, so let's see here. Let's, shut up, watch. Let's double check our calculations here. Okay, so we found that alpha was 20 kiloohms times 10 kiloohms divided by 30 kiloohms, all divided by 2 times 23. I'm going to store that as variable A. So 10,000 over 69 or 144.93. All right, so that checked out. Omega naught was the square root of 1 over 23 times 3. Let's store that as variable B and 0.1204. So that checks out. So S1 is negative A plus the square root of A squared minus B squared. Let's store that as X. 5 times 10 to the negative 5, or excuse me, negative 5 times 10 to the negative 5. So that checks out. Negative 289. All right, so that checks out. Okay, so the only thing I need to be super sure of here, then let's see. So 5 times okay, so all that checks out. All right, so we have in our system solver, it's a 2x2 system. So we have 1A1 plus 1A2 is equal to negative 1,000 over 30 times 10 to the 3. Or negative 33,333 volts. And for our second equation, we should have S1, which was negative 5 times 10 to the minus 5, plus S2, which was negative 289.855. That one is equal to 0.
I can't get the answer to that on app.
So my watch will stop spying on me. I got vastly different answers for A1 and A2. I got, let me do these in blue. A1 to be negative 33,333.339 volts, and A2 to be negative 0.00575 volts. Yeah. So if we
We got a big A with a small S, small A with a big S, so the S1, A1 will equal S.
right, okay. So now C, is 3, times S1, which was -5 times 10 to the minus 5, times A1, which was -33,333.339. Looks like,
Both the A's were negative,
uh-huh,
both of the S's are also negative, right?
that's correct.
Then if you take S1 plus S2, A2, that can't be zero.
A2 is
Okay. 0, 0, 5, 6.
Sorry, yeah, that's actually, A2 should have been positive, small number. There you go, thank you. So let's go back to it. So C was 3, S1 was -5 times 10 to the minus 5. A1 is -33,333.339, which gives me 5, like really honking close to exactly 5.6 zeros, and then 8.5. So I'm just going to call this guy here 5. And then for this coefficient, I'm going to have C, which is 3, times S2, which is -289.855, times A2, which is positive 0.00575, gives me negative 4.99999.8, which is really close to -5. And so they cancel each other out. Let's scratch those guys. Oh, didn't mean to erase them, but that's okay. So now things seem to be working out. Who was it that let me borrow this? Thank you.
we just miscalculated A1 and A2.
Yeah, so A1 and A2 got miscalculated, which in turn resulted in an error in our. So obviously, that means we need to fix this and this. So -33.3 kilovolts plus 5.75 millivolts. And that should be okay. And I should have noticed it, but I didn't. VC at 0 was supposed to cancel out to be 0 as well. Now, this bit cancels this bit, and that bit's so small as to not matter, so it does equal to, well, actually, but we did check it. Yeah, so it would have, it seemed to have worked out either way. All right. So now that we know what IC is, we could go figure out what VR of T is very easily, but I'm tired of doing math without a calculator to check stuff myself. So, all right. I will figure out how to replace the batteries in my TI so that I can do math. And my plan on Friday is to literally just work more example problems. Okay. I may not let you guys choose values anymore. So that things will be slightly more sane. All right. Thank you guys. Hopefully, if you have any questions about this, series RLC circuit analysis, I will be at the tutoring session this evening, Nathan Hall 105 from 4:30 to 5:30. I have placed assignment on parallel RLC circuits on Moodle. I will be putting a homework assignment on series RLC circuits on Moodle here sometime this afternoon. All right, thank you guys.